Good morning, everybody. Thanks a lot to the organizers for inviting me to this very exciting workshop. My name is Paolo Ghelfi. I work in a research center in Pisa, in Italy, where actually two institutes are cooperating. One is Scuola Superiore Sant'Anna, which is a university, and the project I will talk about today is led by Scuola Sant'Anna. And the other institute is Inter-University Consortium. The name is CNIT, which stands for in Italian National Inter-University Consortium for Telecommunication. So I'm sort of double hat on my head. Okay, and this talk we will describe another European project. The title is SPACEBEAM, and these are the main facts about the project. This has started in 2020 as well. It was an H2020 from the call space, which is nice because actually the project is about a solution applying integrated photonics, but the call is space, so it's very application oriented, although it's a research and innovation action. So you will see there are a lot of challenges in this project. The title is SPACEBEAM, which stands for Space Synthetic Aperture Radar System with Reconfigurable Integrated Photonic Beamforming. So we were talking about a lot of the things that we have seen today in the previous presentation. As you all know, the Earth observation from satellite is super important today for a lot of applications, for improving the management of the environment, for understanding and mitigating the effects of climate change, monitoring natural resources, even enhancing the civil security. And the normal way for doing it is to use synthetic aperture radars, which are radar which fly on satellites. And thanks to the fact that they observe the Earth while moving, they allow us to have images at two dimensions, at least in two dimensions, okay? So they have a resolution in both what is called the along track, which is the direction of the satellite, and also across track, the opposite direction. And typically the resolution of a synthetic aperture radar across track is inversely proportional to the width of the illuminated swath. The swath is the strip that is illuminated by the radar itself. There is a geometrical law for which, if you want a large swath, you have to accept a lower resolution. But of course, you would like to have high resolution for understanding, for imaging correctly what you're looking at. But at the same time, you will also like to have large swath for covering as much as possible of the Earth's surface, unless you need to round a lot of time around Earth, okay? So there is this geometric law that gives some limitations. Recently, there have been several proposals for separating the dimension of the swath from the resolution across track. And one of these solutions is what is called the scan on receive, or SCORE, which is the solution that we are looking at. And basically what happens is that the radar illuminates the entire swath in transmission, but the receiver side is beamformed in several multiple beams to cover the entire swath. Of course, you need several beams, and you need to move them because the satellite is moving, and while moving, you need to swap the entire swath. So it's a way for decoupling the swath width from the across-track resolution. This is more or less how it works. You see that there is the illumination beam that covers the entire swath, and then several beams are being formed and moved and steered along the flight in order to cover to receive the entire echo from the Earth. Well, how can this be done in a normal way, let's say using electronics? If we're supposed to have an array of receivers with 12 antennas element and 3 scanning beams, you will need to digitally calculate the 3 output as a linear combination of the 12 input, requiring 12 frequency-specific receiving channels, 1 for each antenna element, and a receiver means a local oscillator, a mixer for the down conversion, a filter or several filters for selecting exactly the bandwidth that you need, and then an ADC to digitally convert the signal. Then you have 12 digitally converted signals, and you have to put them together to calculate the beam forming of the 3 beams, which means 12 by 3, a set of 12 by 3 weights to be calculated. And this requires very large FPGAs, and FPGAs needs power. So basically, all this stuff has prevented the adoption of the scan-on-receive solution with in the electronic domains. And here comes photonics, because photonics can do all that stuff in an analog way, so without using digital, but doing it directly in the analog domain, which also means continuously and precisely, can do simultaneously beamforming and down conversion. And it can also do it with an almost frequency agnostic manner, because the bandwidth of the photonic devices is very broad. We can cover up to 40 gigahertz without going up to the terahertz domain, but still working in the microwave, pure microwave, up to 40 gigahertz. If we do all this stuff with photonics and with integrated photonics, we can really implement a radar receiver in a very small SWAP for SWAP-C format. So size, weight, and power, keep it very low. This is the idea of the space beam solution. The picture that you see was prepared during the proposal preparation. We are still looking at that direction, but then we will see how we are moving on. So the idea is to use hybrid photonic integrated circuits, and then we will see what, in this case, what hybrid integrated circuits means, based on 2 different platforms. One is silicon nitride, and the other is indium phosphide, including active and passive, in order to produce a precise, continuous, wideband, and reconfigurable scan-on-receive beamforming from an array of 12 antennas as input into 3 output beams. And this should allow a resolution in the synthetic aperture radar of 1.5 meter times, sorry, wrong, 1.5 times 1.5 meters, considering a swath of 30 kilometers. This solution would be frequency agnostic in the sense that it can be applied to any radar frequency from 5 gigahertz up to 40 gigahertz. The project will look at X band, so it will work at 9.6 gigahertz, but the technology is ready to cover also Ka. It will also use a novel actuation techniques for what concerns the beamforming that is based on a piezo element deposited on the silicon nitride, which is super important in this case because allows to consume almost nothing electrical power, and also to be very quick in steering the beams. Our goal is to push the maturity of this technology to TRL6, which also requires to do at least some space compliant testing. We will talk about this. And also to realize the entire receiver module. It means the electronics around, also checking if the required electronics for making the board working is available at space grade level. So space beam will show more functionalities, better performance, and lower SWAP than the current systems. At least this is what we claimed at the beginning. This is the architecture, the schematic of how the space beam project works. I will go through it quickly, but I will try to give you the sense of it. you see, we start from a laser. The laser is still integrated as well. All the other stuff here. You see two colors. The green one is the indium phosphide platform. The blue one is the triplex platform. So the laser is half indium phosphide and half triplex, in the sense that the laser is realized as a reflective SOA for the gain element, and then the rest of the laser cavity is derived into the silicon nitride platform. Then there is a modulator, a Mach-Zehnder modulator, that is necessary for realizing the local oscillator. As you see from this sketch here, the idea is to modulate in a double sideband carrier suppression in order to have two tones at a distance equal to the frequency of the local oscillator. They are then split into two. One part is sent directly to the photodiode at the end. The other one is filtered, divided by 12 in order to receive the 12 input signal. And every input signal is loaded on another Mach-Zehnder modulator. And you see that here we have a big block with SOA, Mach-Zehnder, SOA. SOA is a semiconductor optical amplifier. It's an optical amplifier, an integrated optical amplifier. Then the 12 input goes into an optical beamforming network, which realizes the beamforming of the 12 input into 3 beamformed output, where a filter and combiner combines together this signal coming from the beamforming network with a copy of one of the local oscillator, which goes into the photodiode to generate the beating, which gives a beamformed signal directly down converted to intermediate frequency. So a lot of functionalities, and I wrote it down here, challenging number of functions, as you can see. And there are a lot of devices. We have laser, modulators, filters, splitters, SOAs, other modulators. The entire beamforming network is a story by itself. And then photodiode. A lot of things, very challenging. And now I will show you how the project is going on. Here is a closer detail of the beamforming network. The beamforming network is called the blast matrix. It's a from the topological point of view, it is called blast matrix. You see is a matrix with 12 input from the north side and the 3 output from the east side. Of course, we can specify 12 by 3, 36 nodes, where in each node we have basically a variable coupler, realized as a Mach-Zehnder interferometer with a phase shifter to control it, which determines how much of this power is split into one output or the second output, followed by another phase shifter that controls the phase of that part. So in each node, we basically have 2 controls. One controls the splitting ratio, and the other one controls the phase. The structure is simple from the topological point of view, but at the same time, it's complex, because if you think about the path that every signal has to travel, they are all mixed together, in the sense that if you look at the first input on the leftmost side, it can go directly to beam 1 or to beam 2 or beam 3 at the output. It is separated in several different paths. So calculating how the way the controls has to be set in the beamforming network is a trick that requires recursive calculation, but nothing too complex at the end of the day. From the beginning, we ran some simulation to understand this topologies, this scheme, how it should behave. And here are some figures that, by the way, are the same figures of merit that Professor Kamani was talking about this morning. So from our simulation, we have calculated that the output SNR should be around 40 dB, which is enough for this application. The total gain should be something like -5, -6, so we will have a small loss, but not too much. And this is thanks to the presence of the amplifiers. It is relevant to note that the spurious rate dynamic range should be in the order of 55 dB, while the requested is only 32, so much more than requested. intermodulation is pretty low, and the expected power consumption is less than 15 watts, less than 36 watts if we also consider the control electronics. This is a very low number if compared with electronics, with the electronics domain. And again, this is due to the fact that the actuators are done with piezoelectric phenomenon. So it is basically capacitive, and it has no electrical consumption. So where we are now, actually we are a little bit late in the project. It was supposed to end right now in December 2022. We have an extension of 6 months, and still we have a lot of work to do. Unfortunately, as you know, COVID has slowed down everything, and then we also have to face some technical issues that we will talk about later on. So right now we have received from our partner Lyonix the first functional model, which is reported in this picture here. So you can see, well, I also reported the design because maybe it's easier to understand. You see the big block in the middle is the silicon nitride. Then the violet blocks are those in indium phosphide. You can recognize this one is the modulator for the local oscillator. These one are the 3 photodiodes at the output, and this big block is the 12 SOA plus Mach Zehnder plus SOA block that receive the signal from the antenna elements. Then there is also a laser here and some fibers, a lot of fibers actually, 12 fibers on one side and 37 fibers on the other side. And in the picture here is the current state of the art of this project. You also see all the PCB around for the fan out of the signal. And there is also, it's difficult to see, but below this PCB, there is also all the electronics for controlling and driving the beamformer. The test of this architecture has just started, so I don't have much results to show, but just a few, just to have an idea of how things are going on. This, for example, is an example of characterization of one of the filters that we have. Filters are, periodic. And the idea here is to have, if you remember the modulation of the local oscillator, we have 2 lines, so we have to separate one of the 2 lines. The idea is to have one line in the pass band and one line in the stop band, so that in one output we have one line, in the second output we have the opposite line. Here is the first results applying both the local oscillator signal, which is at 8.35 gigahertz, and also the RF signal at 9.65. And you see from here that, what is that? Here is the local oscillator applied to one of the Mach Zehnder. Here is one signal applied to the first input of the array element. All the big stuff is working, so that at the end, from one of the output monitors, we are able to see this graph here, where all the signals can be identified. And after using the internal photodiode, we got the downconverted signal. Yes, we have it. If you take a look at the number, it's minus 77 dB. Okay, no worry. It happens. This is the laboratory life. Why we are not so worried about this number? Because what we need to do is fine-tuning all the components. As we said before, this device is very complex. It has a lot of functionalities. So we are learning right now how to control everything. It is good to see a signal at the end. Now that we have a monitor to look at, we know how to. We have to learn how to trim everything in order to recover that signal at the level that we expect to have. So what's next? Fine-tuning all the components, then characterizing the blast matrix and building the lookup table in order to provide the beamforming, and finally measuring the beamforming capability. We are working on this side of the activity so far. This is not all, of course. In the next 6 months, we have to rush up because we have a lot of things to do. One thing to do is to generate, to realize the second generation of the Space Beam project. The second generation would be a packaged device. And the idea is to have a hermetic package. And here is part of the issues that we have been solving in the last 12 months, more or less. Originally, the idea was to put everything into a gold box, which is probably the standard solution for having a hermetic package. But the point is that it turned out that the ceramic around the photonic part and the gold box itself was so big that it was so expensive, not feasible within the project. So we had to find out a different solution for reaching the goal of having a hermetic solution, hermetic box. And the solution that our partners in Tyndall have found is to substitute the gold box with a chiplet package, which means putting a cap on top of the photonic part and creating the hermetic package in this way. This is a sort of new solution, although it's not exactly new. It is already used in electronics, in the electronics domain, and it seems that it is also being used also in photonics, working. There are some risks associated with that because in the electronics domain, the bottom part is ceramic all over, but instead we have ceramic with a hole in the middle where we have the photonics, and then we have the submount on beneath. So we really need to check if we can do it in a hermetic way. But this is a viable solution. And by the way, it also, at the end, it will be much smaller than the gold box solution. Here is the current stage. The design has been done, so it's on the way. Then another part of the story is to try to see if everything can face the space environment. So we have our plan of environmental testing. There will not be actually a full environmental testing for TRL6, but a significant part of those tests. Here it is reported what we are going to do, and actually we are going to do mechanical and shock and vibration, thermal shock and temperature cycling, terminal strength and bond strength, and also total ionizing dose. Related to the discussion before, this solution is thought to fly at low Earth orbit. So the total ionizing dose will not be that much because the orbit is low, and the timing of the mission should be quite short. So it will not be so heavy as in the case of right? in the previous presentation. But still, we are super curious of seeing what will happen to all this photonic integrated circuit once we put it in the radiation chamber. So, sort of conclusion: what are we giving to the European RF photonics? We have been developing this super complex device with hybrid functionalities. We have already tested the photodiodes, which have a bandwidth of more than 40 gigahertz, modulators in indium phosphide with a tested bandwidth of more than 27 gigahertz, and we have tested it is only minus 5 dB at 40 gigahertz, so it's really capable of working in Ka band, and pretty low Vpi, which it is less than 0.7 at 10 gigahertz and less than 1.1 at 40 gigahertz. Low consuming and fast piezo controls, and hybrid integration of photonics with several functions. And sorry, I forgot to mention, in the packaged version, the fiber will be cut. The fibers, which you have seen in the picture, are there only for aligning, testing, and writing the lookup tables. After that, we can cut the fibers. Everything should work without the fiber. The idea is to put everything into beamforming for synthetic aperture radar. So in order to provide analog, continuous, and precise beamforming with simultaneous down conversion and with multiple beam capability. And this also is pushing the peak maturity thanks to the activity on the hermetic package and the activity on the environmental testing. As I said, a lot of things still to do, but we are working hard and in a rush, as usual. Last slide is a little bit of what's the English for that? Anyway. Yeah, exactly. And positions available. And by the way, not only positions available, I want to draw your attention to this new project. Is a Marie Curie action. So if any students want to apply, you know that Marie Curie are particularly rich in terms of salary. So take a look at that. This Marie Curie action is the name of the project is Microwave Photonics for Space. There are 15 doctoral positions open, 4 of which are in Pisa, 2 under CNIT and 2 under Scuola Sant'Anna. So if anyone wants to have any information, you can write me an email. And by the way, ALTER is part of the same Marie Curie action, again, on space. So as you see, microwave photonics is going to space. Yes, it seems so. And there is a lot of work to do. So talented young guys, raise your hand. We are here. Okay, this is all.